Hi everyone, welcome to OneClass livestream. This is Chang and I'm your senior tutor for today's livestream. Today we're going to talk about some math problems and let's get started. Okay, so let's see our questions here. Our first question is asking us for the linear approximation of the square root of 104. So let's write it down over here. Whoopsie. I think my laptop is being a little slow. Oh. Nice. Cool. So, oh man. I'll try to turn my mouse off to see if it gets better, but my tablet is behaving oddly. Huh. Okay. I'll try to reconnect it. Does it work now? No, it doesn't. Well, I guess I can try to write it on my keyboard like this. Okay, so let's try to do it this way. So we're going to try to get the square root of 104. 104. So in order to do that, we need to use linear approximation. Or I guess they told us to find the linear approximation of the square root of 104. So let's first write down the formula of linear approximation. Again, let's use another color. Oh man, I just wish L of x equals to f of a. In this case, our f of a would be, okay, my laptop is being really odd today. I'm not sure how I could go about fixing it. Oh man. Okay, you know what? I'll just try to pause the video for 10 minutes to see if I can figure out how to solve this problem. If not, I'll just Awesome. Hi everyone, I'm back. I fixed the problem. Yep, I fixed the problem, I think. Okay, so let's do it. Perfect. So again, we're just finding the square root of 104 using linear approximation. So first, let's find out which function we want to use. Since we're finding the square root of a number, we probably just want to use the square root of x because we're finding the square root of a number. Then let's try to find a number that we know the square root of that is really close to 104. The best option we have is probably 100 because we know the square root of 100 is just 10. So this would be a really good candidate for like the linear approximation of the square root of 104 because 104 is really close to 100 and we know the square root of 100. So we know f of a is equals to the square root of a right over there, and we also know a is 100, so the square root of 100 is just 10. I mean, both positive 10 and negative 10 works, but we're just going to do 10 right over here. Okay, and we also know x, which is the number that we would like to approximate. It's 104 because I want to approximate 104 in this case. Next, we just need to write out the function so that we can start the linear approximation. So again, L of x equals to f of a plus f prime of a which is the slope of our linear approximation line, times x minus a. So again, we just need to find f prime of x, which is the first order derivative of f of x. We know f of x is equal to the square root of x, which is also equal to the x to the power of 1/2. Okay, my tablet stopped working again. It's moving really slowly. I guess I'll just wait and write on my keyboard in the meantime. So, square root of x, which is the same as x to the power of 1/2, and f prime of x is just, oh god, we're having a lot of technical issues recently, and the derivative of x to the power of 1/2, in order to find the derivative of this function, we just need to put 1/2 in the front of the expression, and minus 1, subtract 1 from the power of x. So let's write it here. Perfect, so that's our derivative. Okay, and next let's find f prime of a, because we require to find the value of this in order to do our linear approximation. So that would just be 1/2, and our a is 100, and to the power of negative 1/2, which is the same as, oopsie, I hope this, okay fine, I'll just use my keyboard again, which is the same as 100 square root of 100 times 1, or 1/2 times the square root of 100, and we know the square root of 100 is 10, so it's just equals to 1/20. 1/20. Okay, so that's our f prime of a. Now, we have all the information we need, so we just need to plug in the numbers into the equation. So L of x, and again, our x is 1/4, 1/4, 1/4, 1/4, and our f of a, we already calculated over here, is the square root of 100, is 10, plus f prime of a, we already calculated, is 1/20, 1/20, and x minus a, again, we know our x is 1/4, our a is 100, so 1/4 minus 100 is just equals to 4. So it's 4. We also know that 4/20 can be simplified by dividing by 2 on both sides. So 4/20, we just put the 4 on top of the 20 here because they're multiplied together. And 4/4 is just 5, or sorry, 4/4 is just 1, and 20/4 is 5. So our result linear approximation is 10 plus 1/5, which is 10 and 1/5. In fraction form, this equals to 10.2. So if you are more comfortable with fractions, you know that our linear approximation of the square root of 1/4 is just 10.2. Right over here, 10.2. Alright, so that's all we have to do to find the linear approximation of the square root of 1/4. Let's look at our sample solution over here. So the sample solution used the same method that we used, or I guess that's kind of the only method that we should use because they specifically asked us to find the linear approximation. So yeah, they also find the prime, or the first derivative of the function f of x, which is 1/20, which is correct. And yes, they plug in the formula correctly, and they also have the same fraction that we did, or the same decimal that we did, and the same fraction that we did, and we have the same result. So yes, this is correct. So let's just say the solution is correct. Correct. Excellent. Excellent job. Exclamation mark. Nice. Now let's move on to our second problem over here. And I'm just still trying on my drawing pad. Okay, so our second solution over here asks us to use the identity sin x or sin 2x equals 2 sin x cos x to find the derivative of sine 2x. And it also asks us to use another identity or the double angle identity for cos x, where cos 2x is equals to cos squared x minus sin squared x, and it asks us to use that identity to express the derivative of sin 2x in terms of cos 2x. So let's try it. So our second question here, we're just trying to find the derivative of sine 2x. So let's do d over dx of sine 2x is equal to, here they already told us in the question that sin 2x is equals to 2 sine x cos x, so we can just go ahead and plug in 2 sine x cos x into the equation. So we would just interchange sin 2x with 2 sine x 2 cos x over here, because we already know that sin 2x is equals to 2 sine x cos x. My cos is kind of ugly here, but I can't really do anything. And I hope my writing is more or less legible, because I don't have a drawing pad anymore. Okay, and in order to solve this problem, we just use the product rule. So let's do our product rule. The product rule basically states that the derivative of an expression is the first term of the multiplication times the derivative of the second term of the multiplication. So derivative of the second term of the expression. So we have sin x times the derivative of cos x over here. And obviously we still have to times the entire expression by 2. I'll just do a square bracket over here. And we would add that to the derivative of the first expression. So d over dx of sine x times cos x. I'm just going to write it down here because we don't really have a lot of spaces up there. Okay? Next, we just need to do our calculation over here. So we know that the derivative of cos x is just equals to sine x. So right over here we have sine x multiplied by sine x. At the same time, we know the derivative of sine x is equals to negative cos x. So this is actually would be a subtraction sign over here, and then we just put the cos x, drop the cos x term down here, because cos x just stays the same. All right. So in order to simplify this, we have 2 square brackets sine squared x minus cos squared x, and that is the derivative of sine 2x. So we finish our first step here, and the second part of the question asks us to use the identity cos 2x equals cos squared x minus sin squared x to express the derivative in terms of cos 2x. So we know, or since cos 2x is equals to sin squared x minus cos squared x, we know, we know that we can just interchange this part of the expression with a cos 2x. So that our resulting expression would just be 2 cos 2x. Cool, so this is our result. So we know that the derivative of sine 2x is equals to 2 cos 2x. Perfect. Now let's look at a sample solution here. So yes, they have the exact same step as us over here, and they also use the product rule because that's probably what you should do, and the derivative of sine x is equals to cos x, that's correct, and the derivative of cos x is negative sine x, that's also correct. Oh, actually, I read off the question wrong. So they did it in a different order than us. So actually, oh man. So actually, the cos 2x is actually equals to cos squared x. The cos squared x is in front, minus sine 2 squared x. Or minus sine squared x. And over here, the derivative of cos x is actually negative sine x. And the derivative of sine x is equals to cos x. So we actually have a subtraction sign over here. And right over here, we know that we have cos squared x minus sine squared x. We just switch the order of the two expressions. Cos squared cos squared x minus sine squared x. My laptop is just so finicky lately. Okay. So again, the result is still 2 cos 2x, 2 cos 2x. That is correct. Okay. So yeah, this is our result, and we know the derivative of sine 2x is equals to 2 cos 2x. We can also achieve the result directly by directly differentiating sine 2x. We just put the 2 in front, and we apply the rule, and we know the derivative of sine x is equals to cos x. So it will also be 2 cos 2x. But the question asks us to do it using the way, or using trigonometric identities. So that is how we're going to do it. And our sample solution here is perfect. So I'll just say, great. The solution is perfect. Solution is correct. And let's move on to our third problem for today. It is loading. Okay, our third problem for today is asking us what is the square root of 4. And we know 4 is a perfect square, so directly we will just know the square root of 4 is equals to 2. And not only positive 2 times positive 2 is 4, negative 2 times negative 2 is also 4, because a negative number multiplied by a negative number is a positive number. So we know from here that the square root of 4 is just positive 2 or negative 2. Okay, and let's look at the sample solution over here. It is correct. So we'll just say that the solution is correct and move on to our next problem. The solution is correct! Exclamation mark. Okay, now we're on to our fourth problem. Our fourth problem over here it's asking us what is the square root of 1 over 4, or what's the square root of a quarter. So in order to find the square root of a radical, we would just take the square root of the top number and the square root of the bottom number. From the previous question, we already know the square root of 4 is positive 2 or negative 2. And we know that the square root of 1 is positive 1 or negative 1. So this is what our answer is going to be. Again, the laptop is being finicky, but it's fine. And positive 1, or I'm sorry, this should be a 2 over here, and this should also be a 2 over here. Okay? See how I wrote 2 answers here? This is because the positive 1 is matched with the positive 2, while over here the negative 1 is matched to the positive 2. That's why I wrote it in 2 different ways, because there are 4 different combinations. Okay, but this would actually only get us to 2 results, because positive 1 over positive 2 is positive 1 over 1 half, negative 1 over negative 2 is negative 1 half. Similarly, negative 1 over positive 2 is negative 1 half, and positive 1 over negative 2 is negative 1 half. Or sorry, positive 1 over positive 2 and negative 1 over negative 2 is both positive 1 half, and negative 1 over positive 2 and positive 1 over negative 2 is both negative 1 half. So the result of the square root of 1 over 4 is positive 1 half or negative 1 half. Positive 1 or the square root of 1 over 4 is equals to positive or negative 1 half. So this is our solution, and let's look at the sample solution over here. Again, they just did the same thing as us, where they made the square root of the fraction to both the numerator and the denominator. They only gave the answer of 1 half over here, and they didn't include negative 1 half. Again, that depends whether you include negative 1 half. It's depending on your schooling level. In high school, they probably want you to include negative 1 half, whereas in middle school, the teacher would probably be satisfied with just positive 1 half. So I'll say the solution is correct because it really depends on your school level. So I'll just say the solution is correct. It would be better or more comprehensive to also include 1 or negative 1 over 2 as a solution. Okay, and I'm just going to correct the spelling here. Okay, and I'll just say solution is correct. Perfect. Now let's move on to our fourth problem, our fourth problem. Okay, our fourth problem over here asks us how would we calculate the cosine of 3 pi over 2. Again, let's just do fourth problem over here. I'm asking us to calculate the cosine of 3 pi over 2. We know that the angle 3 pi over 2 is actually an angle on the unit circle. So let's draw a unit circle here. This is quadrant 1, quadrant 2, quadrant 3, 3, 2, 3, and our quadrant 4. This is Latin numeral, so it looks like IV because V is 5, and 1 to the left of V in Latin numeral means 1 less. So this is 1 less than 5, which is 4. So these are quadrants, and we know the angle over here is because we start from here. So the angle over here is pi over 2, which is 90 degrees. And over here is another pi over 2, so it's pi. And over here is another pi over 2, so it's 3 pi over 2. So the angle here is 3 pi over 2. This is the angle 3 pi over 2. And over here, we want to know what is the cosine over here. We know the unit circle starts at 1, 0. And then over here, it goes to 0, 1. And here is negative 1, 0. It's just simple polar coordinates. And over here, it would be 0, negative 1. We also know that the x-coordinates on the unit circle represents the cosine angles, and the y-coordinates on the unit circle represent the sine angles. So over here, at the angle of 3 pi over 2, we have x has the value of 0. So equivalently, cosine of pi over 2 would be 0, based on our knowledge of the unit circle. So we know cosine of 3 pi over 2 is 0, and that is our solution over here. Perfect. Now let's look at the sample solution and see how that is. The sample solution, again, the sample solution also tried to solve this problem using the unit circle. And it mentions that, yes, that is correct. But it mentions that the given angle is located at the second quadrant, which is incorrect, because the given angle is between the third and the fourth quadrant, which is over here, and it's kind of far from the second quadrant. So, but the final result here is correct, because the cosine of 3 pi over 2 is indeed 0. So let's just say solution or final result is correct. Final result is correct, but the first sentence of the second paragraph, is this the second paragraph? Yes, it is. Of the second paragraph is incorrect. The angle is located between the third and fourth quadrant, not the second quadrant. The angle 3 pi over 2 is located between the third and fourth quadrant, not the second quadrant. Okay, and let's just say the final result is correct, but the steps are incorrect. So I'll just say it's overall it's incorrect, so that the people review it and change the information or the steps given. Okay, our next question is asking us whether a rectangle is a rhombus, which is a really interesting question. So let's write it down over here. This is I think this is our fifth problem. So in order to find out whether a rectangle is a rhombus, we need to first have the definition of a rhombus. So what is the definition of a rhombus? Or rhombus? So in Euclidean geometry, the definition of a rhombus states that, I don't know why does it say please wait. But basically in Euclidean geometry, the definition of a rhombus is that a rhombus is a geometric shape or a geometric shape with 4 sides the same length. So 4 sides the same length. That is a 4 sides the same length. That is definition of a rhombus. So let's just draw an example of a rhombus. Okay, this is an example of a rhombus, or what a rhombus looks like. Next, let's define rectangle. So again, the definition of a rectangle in Euclidean geometry is a shape that has 4 sides, and all 4 angles of this shape are right angles. 4 right angles. From here, it is obvious that a rectangle is not a rhombus because a rectangle is only required to have 4 sides and 4 right angles, but but the 4th side may not be the same length. So this could be a rectangle and all 4 sides are right angles. However, the 4 sides are not the same because these 2 sides is obviously longer than the other 2 sides. Now, a square is a special type of rectangle where all 4 sides are the same length. In addition, all 4 of its angles are right angles. So a square is a special type of rectangle, and a square is also a rhombus because all 4 sides are the same, have the same length. 4 sides, same length. So from here, the definitions, we know that a square is a rhombus, and a square is a special kind of rectangle, but a rectangle is not a square, and a rectangle is not a rhombus. So the answer over here for this question is a rectangle rhombus? No, rectangle is not a rhombus, because a rhombus requires all 4 sides to be the same length, and a rectangle only requires all 4 angles to be right angles. Now let's look at the sample solution here. They mentioned that a rectangle and a rhombus are both parallelograms, and it mentioned a lot of properties of rectangles, but the only important properties about rectangles is that a rectangle has 4 sides and 4 right angles, or 4 inner right angles. And all the other facts that you need to know about rectangles can be derived from this simple definition. Yes, it mentioned that a rectangle is not a rhombus, but a square is a rhombus. And a square is a rectangle, but a rectangle is not a square. So let's say the solution is correct. Okay, and let's move on to our next problem. Next problem is asking us what is 2.6 as a fraction. As a fraction. So we know 2.6 is a decimal, and 2.6, whoopsie, 2.6 is equals to 2 plus 0.6. We know 0.6 is on the 10th place, so 0.6 in fraction form is 6/10. So 2.6 is 2 plus 6 over 10. We know that 6 and 6 over 10 can be simplified because 2 is a common factor of 6 over 10. So we can divide 6 by 2 and divide 10 by 2, divide 6 by 2, which results in 3, and divide 10 by 2, which results in 5. So we know 10 over, or 6 over 10 is also 3 over 5. It's also 3 over 5. So 2 plus 6 over 10 is equals to 2 plus 3 over 5, which is equals to 2 and 3 over 5. And that is 2.6 as in fraction form. Cool. So 2.6 is equals to 2.2 and 3 over 5. Let's look at the sample solution here. Sample solution here says the same thing, except they didn't simplify 2 and 6 over 10. We also simplified 2 and 6 over 10, and they didn't simplify, but it's also correct. So let's just say the solution can be simplified, but the solution is correct. Exclamation mark. Solution is correct. Perfect. Now let's move on to our next problem. Our next problem is asking us what is the square root of 6 in its simplest radical form. So the square root of 6 in its simplest radical form. So usually how we simplify radicals is we use prime factorization. So we find all the prime factors of a number and we try to see if we can simplify it by knowing all its prime factors. So we know 6 is not prime because 6 can have two factors, 2 and 3, that are not 1. But is 2 prime? Yes, 2 is prime because the only factors of 2 is 1 and itself. Is 3 prime? Yes, 3 is prime. Again, because the only factor of 3 is 1 and itself. So over here we have 6 is equal to 2 times 3. This cannot be further simplified because 2 and 3 are both prime and there isn't really any way we can simplify it because neither 2 or 3 is a perfect square and we don't have repeated numbers over here. So square root of 6 is just the square root of 6. There's no further simplification can be done. So the square root of 6 is already in its simplest radical form. Already in its simplest radical form. Okay, let's look at simple solution here. What is the square root of 6 in simplest radical form? It basically had the same explanation as us. And yes, the square root of 6 is already in simplest radical form. So it's a really straightforward question. Let's just say, great job. The answer is correct. Okay. Let's move on to our next problem. The next question asks us, what is the simplest form of the square root of 112? So our eighth problem here is asking us for the simplest form of the square root of 112. Again, we use prime factorization. So we know that the first factor we can take out is 2 because 2 is a factor of any number or any integers that ends with 0, 2, 4, 6, or 8. So we know 2 is a factor, and 112 divided by 2 is equals to 56. So yeah, we have 2 as a factor. Next, let's look at 56. When 56 ends in 6, so 2 is also a factor of 56. So 56 over 2 is equals to 28. Again, 28 also has 2 as one of its factors, and 28 over 2 is equals to 14, and times 2 times 2 times 14. And we know 14 is actually also has 2 as its factor, and 14 is equal to 2 multiplied by 7. Now, all of our factors are prime because 7 is prime, because the only factors of 7 is 1 and itself, and 2 is also prime. So, this is our prime factorization of 12. Right now, we can collect like terms, so we can collect all the 2's together. There are 4 2's together, so it's 2 to the power of 4. And we also have the square root of 7, because the square root sign follows them. Okay, so we also know the square root is actually to the power of 1/2. So right over here, we have 2 to the power of 4 times 2 to the power of 2 times 1/2. So we have 4 over 2, or 4 times 1/2, which is 2. So our result over here is 2 to the power of 2, or 2 squared root 7, which is 4 root 7. And that is the simplest form of the square root of 112, right over here. Let's look at our sample solutions. Yes, they did it in a very similar way as us, and they had 4 root 7. Perfect. Let's just say the solution is great. You're correct. Okay, the solution is correct. Let's move on to our next problem. The next problem is asking us the square root of 800 in its simplest radical form. Whoa, 800 is a big number. So if we're going to try to find the prime factorization of 800, starting from the smallest number, that's going to take a long time. So another simpler way of solving this type of problem is that we would try to find the biggest factor we can find, then we can like simplify the process. Or we can try to find a perfect square of this number. That way the process of finding the simplest radical form would be faster. But this is not guaranteed to work, because it's not guaranteed to have a perfect square, or it's not guaranteed to have a perfect square, and it's hard. It can be really difficult to find a perfect square by inspection. But in this case, we can find a perfect square really simply, because we know 800 is equals to 8 times 100, and 100 is a perfect square, because 100 is because the square root of 100 is just 10, because 10 times 10 equals to 100. So yeah, in this case, we can do it the simpler way. So then we just separate it into root 8 and root 100. Again, as we talked about, the square root of 100 is just 10. So this is equals to 10 root 8. Again, my laptop is becoming finicky. Let me just... It's 10 root 8. And we know that root 8 can be further simplified because root 8 is not prime. We always need to check whether the number inside of the square root is prime or not. Because if it's not prime, there's possibly simplification that can be done. So we know 8 is actually equals to 4 times 2. Again, we know this by inspection. So 8 is equals to 4 times 2. Times 2. And we know that 4 times 2 . we know that 4 is also a perfect square, so we can put the radical sign on 4. And we also know that root 2 cannot be simplified anymore because 2 is a prime number. So we know that the square root of 4 is 2, so we have 10 times 2 times 2, 10 times 2 times root 2, and we know 10 times 2 is equals to 20, so our simplest radical form, the simplest radical form of the square root of 800 is just 20 root 2. 20 root 2 over here. Okay, let's look at our sample solution over here. They did it the hard way, or probably the easier way, but the way that requires more steps. They just did it by using prime factorization, starting with the smallest prime factor. In the end, we got to the same answer, but the way that we did it requires less step than the way that a sample solution did it. Okay, let's just say correct solution. Great job. Yay, the solution is correct. Okay, now let's move on to our 10th problem. Over here. Our 10th problem asks us what is the square root of 729. Well, from inspection, we know that the square root of 729 is equals to 27. It's a perfect square, but unless you use a calculator or unless you memorize the square root of 729, it's really difficult to just know that the square root of 729 is 27 from inspection. So what we can do is, again, we can also use prime factorization. Prime factorization works in the case of perfect square as well. So again, the smallest factor we can find for 729 is 3. Well, obviously 2 doesn't work because 729 ends with a 9. And 3, we would know whether a number is divisible by 3 by adding each of its individual digit. So in this case, 7 plus 2 is equals to 9, and 9 plus 9 is equals to 18, and 1 plus 8 is equals to 9, and 9 is a multiple of 3. So if the sum of all its individual digits is a multiple of 3, then this number is a multiple of 3. So we know that 3 is a factor of 729, so let's do 3 times a number which is 729. So 729 divided by 3 is equals to 243. Next, let's check to see what's the smallest factor of 243, or the smallest prime factor of 243. Again, we try to check whether this is divisible by 3. So we add all the individual digits. 2 plus 4 is 6, 6 plus 3 is 9, so it's also divisible by 3. So 243 divided by 3 is equals to 81. And from there, we just know that again, we can try to add the individual digits, and we know that this number is again divisible by 3 because 8 plus 1 is 3, and 8 plus 1 is 9, and 3 is a factor of 9. Or we can just directly see that 9 times 9 is equals to 81. So this is our factorization. It's not a prime factorization because not all of this number is prime, but we already know 3 times 3 is 9, so this would just be 4 3's multiplied together. But this would just be 4 3's multiplied together. So from here we can group 1 3 with a 9. So 1 3 with a 9, and another 3 with another 9, which it would equals to 2. The square root of 27 multiplied by the square root of 27. And we know that the square root of if we multiply the square root of 27 together at the square root of 27, and we would know that if we multiply the square root of 27 with the square root of 27, it will be the square root of 729. So similarly, if we multiply 27 by 27, or if we square both sides of this expression, we would know, you know what, let's just square the both sides of this expression. Or actually, let's do this instead. So let's do this instead. So we group the 3's together, and we group the 9's together, and we have, oh, my keyboard stopped working. Okay, and we have the square root of 3 squared and the square root of 9 squared. And the square root and the squares cancel out, so we're left with the 3's and a 9. And 3 times 9 is equals to 27. So again, the square root of 729 is just equals to 27. Also, because it's a perfect square, so the square root of the 729 can also be negative 27. So the square root of 729 is just positive 7 or positive 27 or negative 27. Although we can obtain this answer from a calculator, or we can just do it by inspection, by memorizing the perfect squares up to 27. We can also find our answers using prime factorization if you don't want to memorize it. So yeah, the square root of 729 is just positive 27 or negative 27. Cool. Let's look at our sample solution over here. They just kind of memorized the perfect squares, but you can also derive the answer using prime factorization like us, or like how we just did. However, the solution is correct, so let's just say correct solution. Yay. Now let's move on to our next problem. The next problem asks us, how do we simplify fractions with square roots? Okay, so there are two main types of fractions with square roots. One is like this, and the other type is like this. And the difference is that one type has the square roots on the bottom, and the other type has the square roots on top. Or I guess there's another type that has square roots on both the bottom and the top. So in those cases, the middle case where the bottom is a whole number and the square root is on top, we don't need to simplify those type of fractions because they're already in its simplest form. You might ask why. This has something to do with some complicated mathematics, but also it's just a convention that people use, so no need to simplify. So the convention is that we need to simplify the fraction if the square root is on the bottom, or if the denominator is a square root. and or is if the denominator is a radical, but we don't need to simplify if the numerator is a radical. So this case, the cases on the sides have to be simplified, but the cases in the middle doesn't have to be simplified. Okay, so let's try to simplify 2 over the square root of 6. So how we simplify those type of expression is that we multiply this fraction by 1, or by a number that has the same value as 1. So we know the bottom is the square root of 6, so we just multiply this by another square root of 6, and we put the numerator of this thing, we multiply as square root of 6. So the square root of 6 is just cancels out the square root of the 6. So this expression right over here, also actually has the value of 1. So you're not actually modifying the value of the expression. The value of the fraction stays the same. You're just trying to simplify it by manipulating it. Okay, so on the top, we multiply these two fractions together. 2 times root 6 is just equals to 2 root 6. And on the bottom, we have root 6 times root 6, which is equals to root 36, which is just the same as 6, because 36 is a perfect square. So it just equals to 6. It's just equals to 6. Oh, my finicky laptop. Okay, and this number is equals to, and we can further simplify it by you know what? I think it might be Bluetooth connection. No, it's just my laptop. Okay. And we can further simplify it because we have 2 on the top. So we divide by 2, which is 1. And we have 6 on the bottom, which 2 is a common factor of 2 and 6. So we can divide 6 by 2 as well. So we have 3. And the final result over here is equals to root 6 over 3. And that's our simplification. And now we can see that our fraction has the form where the numerator is a radical and the denominator is no longer a radical. Again, now since the numerator is a radical and the denominator is no longer radical, this fraction is in the category of no longer need to be simplified. So this is a simplified version of our fraction, and this is how we simplify fractions with square roots in it. Okay, so this is how we solve this problem. So basically, when you encounter the fractions that contain square roots, if the square roots is on the numerator only, then it's already in simplest form and you don't need to do any simplification. But if the square roots is in the denominator, then you need to get rid of the square roots as much as possible. So yes, this is kind of the rule of when to simplify fractions with square roots. Now let's look at the solutions here. Yep, they stated the rule of when to simplify fractions, and they had the same example as us, and they also simplify it step by step. Perfect. Let's just say perfect. The solution is correct. The solution is correct. Okay. Solution is correct. All right. All right. So that concludes our live stream for today. I hope you enjoyed it. Again, really sorry about the problem, whether it's because of my mouse or like my tablet. I'll try to figure it out. I don't know. I'm just having so much technical issues recently. But yes, thank you a lot for watching, and I hope you enjoyed it. Have a great day, and I hope to see you again in OneClass live stream in the future. Thanks!